Welcome to another course of continuing education for professional engineers. This course will focus on liquefied natural gas vaporization. When I first started this course, I thought, well, it's not too exciting, vaporization, but then I realized vaporization is the most critical function of an LNG facility other than an export terminal. Export terminals take LNG and put it onto ships and send it out. A few LNG facilities to make LNG, store it, and put it into trucks and ship it out. But almost every other LNG facility, be it an import terminal or a peak shaver or a satellite facility, takes LNG, stores it, and then when it's needed, they vaporize it. And it's extremely important for that vaporization system to be ready to operate when needed. A little bit of information about myself. I'm a PhD in mechanical engineering. I have a master's degree in both mechanical engineering and civil engineering. I've taught undergraduate and graduate level engineering courses at a university level. I have 52 years of gas industry experience. I retired from Keyspan Energy in 2004 as Vice President and Chief Engineer. Today they're known as National Grid. I have 20 years of international and domestic experience in teaching and consulting on LNG projects across the country and around the world. I have a passion for LNG safety, for developing human resources, and for ensuring that our gas industry is reliable. The learning objectives of this course will be to give you an understanding of what vaporization is. The energy requirements for vaporization is two types of energy requirement. You have to put heat into the LNG to convert it from a liquid to a gas, and also you have to pump that LNG from tank pressure up to the distribution pressure and account for any pressure drops that will occur in the piping as well as in the vaporization. You'll learn about pump curves. We'll look at pump curves and how very important they are to understand them. The importance of vaporization reliability. And there are many facets of that we will touch on. The types of vaporize, the pros and cons of each, concerns that you have during vaporization. How fast can you swing a plant into the vaporization mode? If you get a call that there's an emergency and gas needs to get on the system right away, how fast can you get that plant online? Vaporization capacity constraints. There will be constraints to how much you can vaporize due to certain variable conditions. The maintenance of vaporization equipment, and most importantly, single point failure modes. Single point failure modes are modes that can shut down an entire plant based on a single failure of a component. Vaporization reliability is a mission-critical role of the LNG plant. Without such reliability, gas outages of end-use customers could occur, and this could potentially lead to catastrophic consequences. Vaporization transforms cryogenic LNG to gaseous vapor to be used in the natural gas distribution system. If the LNG vaporization is unavailable when needed, insufficient pressure may happen in the gas distribution system. And this may force the local distribution companies to shut down large portions of their service territory, and this is to avoid flameouts and subsequent gas flowing into buildings. To complicate matters, LNG vaporization is typically needed during the coldest days of the year. Any home with a loss of heating during these periods can be at risk for serious property damage or serious risk of life and health. Restoring gas service after a gas outage is extremely expensive, long-lasting, and challenging. And this is because each gas appliance must be shut off before the gas can be restored to that appliance. This is a graphic that shows what happens when you liquefy LNG. You basically cool it down and make it from a very gaseous form or from a very non-dense form into a very dense form liquid form and stored as a liquid. And then when you vaporize that LNG, you add heat to it and it expands, it converts from a liquid to a vapor and expands until it's at the distribution temperature and pressure and then goes out to the end use customers. The criticality of having vaporization systems be reliable is dependent upon the type of LNG facility that we're dealing with. If it's an import terminal that is dedicated to a single customer, like an electric power company that's producing electricity, it's exceedingly important because if you cannot vaporize, you cannot produce electricity. If it's an import facility that has multiple customers that are being supplied with vaporized LNG, again, it's extremely important. Without vaporization capability, that facility cannot supply the gas to the required customers. An export facility, vaporization is not important for an export facility because they typically don't do any vaporization. They typically just liquefy gas, store it, put it on ships, and send it out. Satellite facilities and peak shaving facilities are exceedingly important that their vaporization systems be fully reliable. Keep in mind the function of a satellite facility is to maintain gas supply in an area. And for a peak shaving facility, it's during the coldest days of the year, the highest demand days of the year, to be available with gas supplies to supplement the requirements of the customers in that area. In a gas outage, pressure in the system that's supplying the end use customers, starts to drop. As that happens, there are appliances like a kitchen stove that do not have a thermocouple or a thermal sensor that would shut off the gas if the flame goes out. So if you get flame outs on some of the appliances and it does not have an automatic thermal shutoff, when the gas pressure resumes, comes back onto the gas main, gas will start entering buildings and then you can have explosions. It's an extremely hazardous situation. So to prevent that hazard from being widespread, what will often happen is that an LDC, a local distribution company, will intentionally sacrifice a section of their territory and totally close the gas off to that section of the territory to use the gas that would have been in for that section to keep pressures adequate within the remaining section of or the remaining part of the gas system. Doing that now leaves this section without gas, and that section has to be relit. In order to relight a gas section of a gas outage, you need to get to every single appliance before bringing gas onto the system. To shut off that appliance, let's say that stove, you need to shut off that stove so that you can now bring gas back. Now, what's typically done is the house has an external shut-off valve. You just shut off that external valve, and every appliance in that house will not see gas once gas is restored. However, in many locations, external shutoffs to the house are not accessible. In particular, in large cities, where there are no external shutoff valves, typically low pressure systems. So in those cases, you have to get into every single house and shut the appliance off. If you cannot enter the house because people left because there was no heat, then you need to dig a hole outside the house and physically disconnect the service from that house, from the street to that house. Access to the buildings may be difficult because people leave during an outage. They go to live with relatives or go to a shelter or to a warm place where they can at least rough out the cold weather. Bringing gas to back to each appliance is also difficult because now you have to be able to gain access to each appliance. So if the customers are not home, you have to leave that building totally shut off. And once you can gain access to every appliance, then you can bring gas back to that house. So let's say it's a 10 apartment building, and you're able to gain access to 9 apartments. Well, that 10th apartment you have to get into before you can bring gas onto that building. The total relight could take weeks, even months. The economic and public welfare toll could be catastrophic. For elderly people or those that are ill and bedridden, a gas outage with the house getting cold and freezing water piping can be a life and death situation. The LDC's reputation will be extremely hurt, and there will be economic consequences as well. This is a pressure enthalpy diagram for the mixture of 95% methane, 4% ethane, 1% propane. As you can see, the curve consists of a dome, and the dome is really, this is the saturated vapor line. This is the critical point. This is the saturated liquid line. Now, I overlaid some red lines on here. This is all subcooled LNG. This is a mixture of liquid and vapor LNG. This is a superheated vapor. It wouldn't be called LNG anymore because LNG is liquefied natural gas. So this would be natural gas or vaporized LNG. This would be a mixture of vaporized LNG and liquid LNG, and this would be subcooled. Now, the word subcooled means that it's colder than its boiling point. So let's pick a pressure here. This is 100, 200, 300 psi. At 300 psi, the boiling point of LNG is just under minus 160 degrees Fahrenheit. At atmospheric pressure, which is 14.73 for this mixture, it's somewhere around maybe 257, something like that, degrees Fahrenheit. And it really depends upon a pressure-temperature relationship as shown here. So let's say we start off with a tank that's at 16.5 psi absolute, and that's a typical tank pressure, and that's about minus 256 degrees Fahrenheit. And you can see that if you pump up that LNG, it pumps into the subcooled region. And in this case, I'm neglecting pressure drops, and I'm neglecting the fact that I have to go through a control valve. So I'm just saying, let's say I had 100, I pumped up to 100 psi absolute, and then I heated it up, added heat to the LNG. And as I add heat, it goes from subcooled to saturated LNG, add additional heat, and starts to boil, continues to boil off, and becomes a saturated vapor. And then I continue to add heat, and it becomes a superheated vapor. And now we're in the superheated range, and I chose to bring it to 40 degrees Fahrenheit. That's the 40-degree Fahrenheit line that's shown here. And the reason why I chose 40 degrees Fahrenheit, because that is the typical output temperature of vaporization processes in LNG facilities. And why do you not bring it up to 60 degrees? That's just wasted energy. Why not down to 30 degrees? Well, if the piping is going to go underground, you may end up freezing the soil around the piping and get frost heave. And so 40 degrees is a typical good temperature that you operate a system at, a vaporization system at. Now, I particularly chose 100 psi because that's a nice pressure for a LDC, a local distribution company, to use to feed into their systems. Now, you could be feeding a transmission system at a much higher pressure as shown here. Now notice you do not go through the dome. So you do not experience a liquid vapor interchange because above the critical point, which is shown here, this is the critical pressure shown here. Above that critical pressure, there is no liquid or vapor. It's just a fluid. Below that critical pressure, you have liquid and vapor. So you have liquid and vapor existing, and you'll go through that boiling process. But above the critical point, it's strictly just a fluid that heats up. So here I'm heating up a fluid from this pressure at 1,000 psi. I'm heating this fluid up to 40 degrees Fahrenheit. Here I chose to go to 1500 psi absolute and heat it up and come to a fluid of 40 degrees Fahrenheit and pressure of 1500 psi. Take notice, these distance of these lines gets shorter as you go to higher pressures. So we're actually requiring less heat to bring it up to send out temperature as you go higher in pressure. On the earlier slide, I showed you information about this mixture of LNG in a graphical form. Here I'm showing it to you in a table form. If you look at this table here, we see LNG at 100 psi and at 100 psi and minus 254 degrees Fahrenheit. We also see that LNG at 100 psi and 40 degrees Fahrenheit. And if we look at the enthalpy, that's this here, the enthalpy, look at the change in enthalpy, we'll see how much energy we have to put into that LNG to go from minus 254 up to 40 degrees Fahrenheit. So looking at that change in enthalpy, we see for the 100 psi shown here, it comes out to a total of 363 BTUs per pound. And if we look here, we see that as you go up higher and higher in pressure, it requires less energy to convert it from its initial temperature to its final temperature of 40 degrees Fahrenheit. And here you see it being done for 1,000 psi, going from minus 251 to 40. And here you see it going from minus 249 to 40. And this is at 1,500 psi. And you might ask why this is slightly warmer. Well, don't forget we have pump work going in. Now, I did not calculate these temperatures, but I guesstimated them from my experience. And you'll see they're pretty close when you go through calculating the actual temperature of the LNG that comes out of a pump. The only reason why the temperature of the LNG that comes out of a pump is warmer because you're putting work into it. You're putting work energy into the fluid. And then we have to ask about, well, how many pounds of LNG is going through the LNG facility or through the vaporizer? Well, to do that, you need to know how many pounds are going through, how many standard cubic foot would that represent. And we can find out how many standard cubic foot are in a pound of LNG by looking at the standard conditions, 14.73 and 60 degrees Fahrenheit. And we can see that the density at those properties is 0.043552. We divide the density into 1, you get the specific volume. So if you take this number divided into 1, you find out that there are 22.96 standard cubic foot in a pound. Now we have a vaporizer. We need to vaporize, let's say, at 10 million standard cubic foot per hour at 100 psi. Well, that would require 10 million divided by 22.96. Let's times that by the 363. That's how many BTUs per pound is required. It would require putting into the LNG 158.1 million BTUs every hour into that LNG. Now keep in mind, vaporization systems are not 100% efficient. So because of that, you have to select an efficiency. Let us say our efficiency of our vaporizer is 80% efficient, meaning that 80% of the energy that is put into the vaporizer as fuel comes out as heat added to the LNG. That means that instead of needing 158 million BTUs per hour, I need 198 million BTUs per hour. So nominally, this would be a 200 million BTU per hour heat input vaporizer. On the earlier slide, I showed you that a pound of LNG would produce 22.96 standard cubic foot of vapor. And that's for the mixture 95-4-1. That's 95% methane, 4% ethane, 1% propane. For a 10 million standard cubic foot per hour vaporizer, take this 10 million divided by 22.96, and we end up showing that we are required to move 435,540 pounds of LNG through this vaporizer per hour. If we had an isentropic adiabatic pump, that would require 402,426 BTU per hour of work input going into the pump. And if that pump was 80% efficient, then that 402, 426 would really be 503.33 BTU per hour. That's shaft work going into the pump. At 25-45 BTU per hour, equaling 1 horsepower, that means I'd require about just under 200 horsepower. So using a nominal 250 horsepower motor would be adequate, but we'll find out later why it's better to select 3 125% horsepower pumps. That's 3 50% capacity pumps rather than a single 100% capacity pump. Let's go back a moment and see where we found this 0.92397 BTU per hour of BTU per pound that's required to raise the pressure of that LNG. Take a look first at what we rose the pressure from to. We went from 16.5 psi absolute, and that's tank pressure. And I know I want to get my vapor out at 100 psi absolute, so I selected 150 psi as the outlet pressure of the pump. And the reason it's higher is because we have to go through a control valve to control how much LNG we're vaporizing. So we need a pressure drop across that control valve. And we also have a pressure drop within the vaporizer itself. Now, to make it adiabatic isentropic, you make the entropy be exactly the same. So the input for the second line is you put the pressure in and you put the entropy in, and the rest of the line populates through the software. And looking at that, we then take a look at the enthalpy. The change in enthalpy is where I get this 0.92397, and then you know the rest of the calculations as shown here. Before leaving the topic of pumps, I want to touch upon the different types of pumps and the different configurations. Many of the newer tanks, in fact, most of the newer tanks, have no bottom penetration, and the pumps are inside tubes so that the pumps are submerged 100% of the time. So you might have four tubes with three pumps, with three of the tubes having pumps, and the fourth is just a spare tube, but you have three different pumps available for use. The key with this is that these pumps are always submerged in the LNG, and they're always ready for operation. Pump cool down typically takes about 12 hours. So it's an advantage to have the pumps continuously submerged. Now, even if you have a bottom penetration on your tank, you can have the pumps continuously submerged in LNG. There are two different types. You could have where the pump is continuously submerged and there's a shaft that comes out of the pump, goes to a motor, and that motor drives the pump. That's the least popular because you have to deal with pump seals, and you have to deal with the potential that if you have a seal, you could have a leak, and then there's problems associated with that. Many of the pumps that are external of the tank are actually motor and pump submerged in a liquid inside of a what's called a pump can. So these be exact same types of pumps, but instead of being installed in a tube that goes into the tank, they're installed in a can that's outside of the tank.
Federal Energy Regulatory Commission white paper on interchangeability is pretty much the golden rule that's used across the industry for determining whether a gas is interchangeable. When you make LNG, it's not the same as pipeline gas. Components are taken out of the LNG, and then LNG is produced. And then when you vaporize that LNG, it has to be interchangeable with the existing pipeline gas so that the customer's equipment can operate properly. Some of the guidelines for interchangeability are as shown here. The higher heating value of the gas should be below 1,110 BTU per standard cubic foot. We'll define what a standard cubic foot is. The Wabi number must be below 1,400, and that's a unitless value, the Wabi number. Inerts must be below 4%. C4 plus components must be less than 1.5%. And these are all, when I talk about percentage, mole percentages, not mass percentages. And I mentioned two things, Wabi index and standard cubic foot. So first, let me talk about a standard cubic foot. It's a cubic foot of gas, 1 foot by 1 foot by 1 foot, that it happens to be at 14.73 psi absolute, 60 degrees Fahrenheit. And the reason why I say it happens to be at, because not everybody defines a standard cubic foot in the same temperature and pressure. For instance, Henry Hub defines it at 59 degrees Fahrenheit, 14.73 psia, but 59 degrees Fahrenheit. All the engineering companies, I shouldn't say all because that's too all-inclusive. Let's say most of the engineering companies that build LNG facilities use 14.696 psia and 60 degrees Fahrenheit for standard temperature and pressure. So the standard temperature and pressure that's used for the gas industry in the United States is, as shown here, 14.73 and 60 degrees Fahrenheit. And the Wabi number, that's a unitless number, which is the higher heating value of the gas divided by the square root of the specific gravity. And the higher heating value is the amount of heat that is rejected from a fully combusted gas, a gas that has gone through complete combustion with the exactly stoichiometric amount of air and the amount of heat that's extracted from that gas to bring the initial gas from 60 degrees Fahrenheit, that was the initial components of gas and air, through the combustion process and bring it back down to 60 degrees Fahrenheit, which means any water vapor that was produced during that combustion process gets condensed out. I mentioned weathering on the slide earlier, and I didn't explain it. So let me go over what weathering is. As your tank sits there idle, no pumps are running, and your tank is just gaining heat from the environment, boil off is occurring, meaning that some of your LNG is converting from liquid to vapor. What boils off? Essentially a most volatile component. So that would normally be, if you had nitrogen in your gas, would be nitrogen. But let's take a tank that has no nitrogen content. So methane would be a most volatile component within the tank. Methane would boil off, leaving behind the ethane, propane, and any other heavier hydrocarbons. So in this case, we're going to start off with a concentration of 93% methane, that's C1, 5% ethane, remember that's a bit high, that's C2, 1.84% C3, which is propane, and a small amount of the heavier hydrocarbons, C4 plus. I said there's no nitrogen in this LNG, so that gives us a total molar content of 100%. So now what happens as weeks go on, days go on, some of this methane boils off, and you see the methane concentration getting less and less and less. But the molar concentration of ethane remains the same, and the propane remains the same, as does the heavy hydrocarbons. Well, what does that do to the higher heating value? Take a look here. Higher heating value starts off at almost 1080 and ends off here at 1085, and that's in week 23. And the Wabi number, as shown here, goes from 1393 up to 1397. We're bumping right up against that 1400 limit that FERC requires. So this is what weathering is. And on the next slide, we'll look at it, taking it to from week 23, we'll take it to week 52. Continue with this spreadsheet looking at how weathering affects BTU value and Wabi number. Week 24, we're at 0.85 moles of C1. If you remember, we started off with 0.93 moles of C1. We're looking at 0.05 moles of ethane and 0.018 4 moles of propane. Wabi index is 1397 and higher heating value is 1086. Over time, let's look at week 52. And in week 52, the higher heating value has raised up to 1095, quite high, and the Wabi number is now 1402, which is in excess of what's allowable by the FERC guidelines. Let's take a look at what has happened to the mole percentages of the different components. Here we have 91.4% methane, 6.1% ethane, and 2.2% propane. What has happened is preferentially the methane has boiled off, the ethane has remained the same, and the propane has remained the same. Thus, if you look at the total mixture, you see that it is now a lesser percentage of methane and a higher percentage of the higher heating value components of ethane and propane. And that's why when you're selecting a site, you have to make sure that your feed gas is appropriate for the LNG that you want to make. And if it's not appropriate, you're going to have to do some more pretreatment. The more pretreatment you do, the more costly the plant will be.
Since the purpose of the LNG facility is to provide send-out when needed, the send-out has to be connected to the load center by way of a pipeline, a discharge pipeline. Ideally, there'd be two discharge pipelines in case one is not available due to maintenance or due to damage. But at least a single pipeline connecting you to a load center. And it's important that that pipeline have sufficient takeaway capacity. Takeaway capacity not only for peak hour, but also for min hour. For instance, if I have a 10 million per hour vaporization system, and I'm expecting to be able to supplement my daily supply by the amount of 240 million on a peak day. I want to make sure that that's 10 million can be taken away from the plant, both on not only the peak hours, but during the minimum hour flow hours of the day. So the peak hour might be 6 a.m. in the morning, and your min hour might be 1 a.m. in the morning. You want to make sure that you have that complete takeaway capacity. And the way to do that is you do a system analysis using modeling, computer modeling of your gas system loads, as well as your piping network capability to remove gas from that LNG plant.
Site selection is typically very closely correlated to the type of vaporizers that you select. Submerged combustion vaporizers are very efficient and very easy to use, very forgiving. However, there are some negatives associated with them, such as it's hard to get the emissions down to the requirements that are listed for some areas of the country. If you're in a non-attainment area, you would typically not use submerged combustion vaporizers unless you use a significant amount of post post treating of the exhaust gas. Also, submerged combustion vaporizers produce acidic water that needs to be treated and managed. There are also boiler and remote heat exchanger type of vaporizers. These have a higher capex, but the heat exchanger can be placed within the impound basin of the dike area if you're using a single containment tank. And that's a real plus because it contains all of the LNG carrying material within the dike area, and that is a significant plus from a safety and a siting standpoint. Then there are the indirect fired water bath vaporizers. That is where the indirect fired uh, boiler and the LNG tubes are all within the same water bath, but the firing mechanism and the LNG inlet are in close proximity to each other. This is a sketch of a submerged combustion vaporizer. You burn natural gas, and the products of combustion bubble up through the water. In doing so, you get a very high efficiency heat transfer because the products of combustion are actually condensed. And that condensing of the H2O that's in the products of combustion, of course, the CO2 is not condensed, but the H2O is condensed. So you have excess water being produced. And because there's CO2 in these bubbles, you end up with carbonic acid being produced. And that carbonic acid makes the water acidic, so this water has to be treated, but it also makes the water corrosive to the materials within the water bath. So there are pros and cons to submerged combustion vaporizers. They're easy to operate. Their emissions are typically not as good as boiler uh, emissions, and the acidic gas that comes out causes the water to become acidic, and therefore causes you to have to treat the water before disposing of it. Then you have the boiler heat exchanger type of vaporizer that's shown here. The boiler is not shown, but essentially you have hot PEG or WEG coming into the shell and being sent back to the boilers here. And at the same time, you have LNG coming into the vaporizer, being heated up and coming out as natural gas here, or I should say vaporized LNG, and going out to the customers. The way this is controlled is you measure the temperature here, and when you measure the temperature here, you control the amount of hot WEG or PEG that is sent to this vaporizer. And what is PEG? It's propylene glycol. What is WEG? It's water ethylene glycol. This is the indirect fired boiler water vaporizer. And what it is, you see that back, you can't see it back here, but behind here is a burner that sends flue gases down a tube. and then returns them through other tubes. And this is all sitting in, and then the exhaust coming up here. This is all sitting in a bath of propylene glycol, and that propylene glycol is heated up. And as that propylene glycol is maintained at a certain temperature, your LNG is fed in through this heat exchanger, goes through these tubes, comes back, comes out as natural gas here, which is sent to the customers. There are also process heat vaporizers, and this will use heat from a process. And again, we're talking about site selection. So if there's a process nearby that has a lot of excess heat that they are getting rid of, let's say you have a power plant, you can set your facility next to that power plant, make arrangements to use that waste heat to drive your vaporizers if you're going to be in a vaporizing process. Or if you're self-generating your electricity, you can use your waste heat from your electric generation to drive a process vaporizer.
This is a picture of two ambient vaporizers, and you can see they're nothing more than fin exchanges where air is circulating through the fins and LNG is going through the tubes that are attached to the fins. The big negative about ambient vaporizers is that if it's cold outside, you can't get enough heat out of the air to bring your LNG up to the 40 degrees required, and then you'd have to put a trim heater on it. Also, it's a negative about ambient vaporizers is they tend to collect a lot of frost over them, and that hinders the heat exchange. And eventually, you have to warm up the vaporizer to get that to remove that ice that builds up, and to get back to your design heat transfer of the capability. So ambient vaporizers have their place, but they're very limited. In this particular picture, they're being used for a portable installation. It was a portable vaporization site that was used to hold up the gas demand while maintenance was being done on the supply piping. Open rack vaporizers use warm water to vaporize LNG. It's typically seawater, so it's only really good in the southern climates where the ocean waters are above 80 degrees a good part of the year. And there are some positives and negatives to open rack vaporizers. On the positive side, the energy for heating the LNG is free energy. You're taking it out of the ocean and you're cooling that water down and putting it back into the ocean. So that's all free energy. On the negative side, you need a lot of pumping capacity because you're going to need to move a lot of seawater in order to do the vaporization. And the reason why you need to move a lot of seawater is because, from an environmental standpoint, you cannot cool the water down too far. Typically, the requirements are you must put the water back no colder than 4 degrees colder than what you took it out of the ocean at. So if you took the water out of the ocean at 80 degrees, you'd have to put it back at something warmer than 76 degrees. And also, there's a lot of marine life associated with seawater, so you need to strain that out and discard the marine life, hopefully not damaging any of the marine life, not killing any fish, etc. So you have to put in large screens that would avoid catching fish and other organic living creatures into the water system that's going to be used to do the vaporization. You need to also realize that the seawater is corrosive, and marine bacteria and marine life can start growing within the piping systems, within the straining systems, and within the open rack vaporizers themselves. So that requires constant cleaning. Water management issues for open rack vaporizers are significant. You typically have to design it with very large diameter piping because you're going to manage a lot of water, large circulation pumps, You'll have to make sure that your piping is such that the outlet going back into the ocean is not near the inlet coming from the ocean. This way, you don't end up cycling the water from the return line back into the supply line going to the plant. You'll have to have a significant amount of screening and separation, backwash capabilities to make sure that you're able to clean these screens and filters. And with some plants, they'll actually dose the water that's coming into the plant with hypochlorite in order to remove or to eliminate some of the organic material that can grow on your plant components, like your filters, your pumps, and the vaporizers themselves. This is a hypothetical plot of the heat transfer over the length of the heat exchanger for a open rack vaporizer. Now, earlier I said that you have to have a 4-degree Fahrenheit maximum delta T of the water that you take out of the ocean versus the water that you bring back the ocean. It's really country dependent and location dependent, local. So it's up to the environmental requirements of the area that you're working in. I said 4 degrees Fahrenheit earlier. For this particular plant location, it's 4 degree Celsius. That is the requirement. So you can see the seawater has a very slight change in temperature as compared to the LNG, which has a very large change in temperature. LNG changes in temperature about 300 degrees Fahrenheit, and the in this case the seawater only changes in temperature by 4 degrees Celsius. So that means that you need to move a lot of seawater, and you can see the profile of the delta T between the seawater and the LNG output. I mentioned reliability early on in this presentation, and there are just so many topics on reliability we could discuss. So I just put together a really simplified conceptual vaporization system just to show you some of the areas where reliability can be hindered or can be helped. Let's take, for instance, I have a tank. Well, the fact that I said a tank, that in itself is a reliability issue. If you only have one tank and that tank gets damaged, there's no way that you're going to be vaporizing if that tank has to be taken out of service. So, of course, the more tanks you have, the more reliable your LNG facility will be. But that's only one component of vaporization reliability. So let's say I call this plant, and it happens to be a bottom withdrawal plant. I call it online, and when I call for it to come online, this internal tank valve won't open. There's a reliability issue, and it's a single point reliability issue because I only have a single tank with a single internal tank valve. So even though I have 3 LNG pumps, 3 vaporizers, 3 odorizers, I cannot open this internal tank valve. I cannot operate the plant. So one of the ways that you can open an internal tank valve if it won't open automatically is it has a manual override where an operator can come up to the top of the tank, pump up the valve, and open that valve. But if that did not open automatically, it's probably because there is an ESD that has to be cleared. And if that ESD doesn't open up this valve, that ESD is probably stopping other parts of the vaporization system from not operating. So the internal tank valve by itself is an issue, but it may be a symptom of a much bigger issue like an ESD that's in progress. What about this valve? If this manual valve, if the stem breaks on it and it won't open, well, that's a single point failure that would not allow you to vaporize. How about this motorized valve? Same holds true with this motorized valve. And I shouldn't say motorized, I'll say power operated valve. It could be an air operated valve, it could be electrically operated, however it's operated. I show here now I have 3 pumps. Now, what's good about having 3 pumps is that if one pump fails, I have 2 others. Typically, we would have 3 50% pumps so that if I lose one pump, I still have 100% capacity of vaporization. And typically, it's good to have 3 50% vaporizers. So if I lose one of these vaporizers, I will still have 100% vaporization capability. Now, let me mention something here that's not shown, and that is, let's say I lose this pump and this vaporizer. Well, because there are no bypass lines or crossover lines, I should call them, across from the pump to pump, I cannot use this pump to feed this vaporizer. So what would make this even more reliable is to put crossover piping between these pump outlets so that if one pump is down, I don't lose the entire train of pump and vaporizer. Let's take a look further downstream. I have another single valve, another point of single failure. And you can see there's a whole slew of single valves here that can give me single point failures. There's another one here that's of concern, and that is that I have 3 odorizers. Why 3 odorizers? To make sure there's redundancies. And I have 3 lines going from the odorizers to the gas main. This is a good thing. However, I have a single injection point. If that single injection point were to freeze up or plug up, I would now not be able to vaporize. There are more things that we'll talk about, but from a design standpoint, you need to build in reliability. I have a single electric feeder coming into this plant, and a single electric substation, and a single motor control center, and a single feed from the motor control center to the pumps. A single plant control room with logic controllers that will control the processes. Any one of these components can be a source of shutdown of the plant. And you need to build in redundancies to make sure that by design your plant is reliable. I also mentioned a lot of this in the reliability by design slide, but let's go over some of the redundancies that I've built in here. 3 pumps, 3 vaporizers, 3 odorizers. But there's only a single pipeline outlet from the tank. Ideally, I might have 2 outlets from the tank to this header. That would be a better choice, but it's an expensive choice, and it's not one that you can make after the plant is built. You might be stuck with what you have. So just understand that redundancy gives you a lot of ability to overcome some kind of a malfunction, but it has its limitations. What else? What else could we do that's redundant? A single electric feeder. That's a concern because this might be fed off of telephone poles that, or I should say, electric poles that are supplying the plant. So your one car accident that'll knock down an electric pole away from your plant not being functional. So you may consider having 2 feeders, one coming in from this side of the plant and one coming in from another side of the plant. Substation, well, maybe if you have that second electrical feeder, you'll have one electrical feeder that feeds 2 of these pumps and the other one feeds a third pump. Or you could have all of them being capable of being fed off of either substation and off of either electrical feeder. You have a single distribution piping, or maybe you'll have multiple outlets to this plant that'll feed different distribution system, different parts of the distribution system. Maybe one set of piping will feed into a 250 psi line. Another set of piping will feed into the 60-pound system. Another set of piping will feed into a 125-pound system. Now, all of this is increased capex and opex, but it's the type of thing you want to consider when you're talking, the type of things that you want to consider when you're talking about increasing reliability. Remember, the cost of an outage is a lot more expensive in many ways, not only in dollar cost, but in the reputation of your company and the welfare to your customers. Next, we'll talk about reliability by control. There are many, many PLCs, programmable logic controllers in your plant, or you may have a DCS, a distributed control system within your plant. And those need to be programmed by people who are skilled in programming but also understand the process. And a single error can cause a plant shutdown or cause you a loss of control. And that can also be true if you just operate the plant improperly. But let's talk specifically about controls. Let's take your pumps. Well, your pumps will only go on if they have an interlock on them, or they should have an interlock on them that says your pump will start in recycle. If your recycle valve is not open, your pump will not start. If your recycle valve is for some reason in the wrong position, you have trouble starting the pump, well, certainly it might have an interlock that says the inlet valve has to be open first, and this inlet valve has to be open first before you can start a pump. One of the biggest concerns is if you start a pump and you burn out that pump. Now, your natural instinct is, okay, I'll use the other pump. You go to restart the second pump. Don't jump to that too quickly, because you got to find out the reason why the first pump burnt out to make sure you don't burn out the second pump. It has happened where the operator burns out the first pump, then burns out the second pump, too afraid to do anything else, calls a supervisor over. Supervisor comes, turns the third pump on, and it burns out. Now you have no capability for vaporization. So you need to make sure that when you're operating your plant, you're operating it well with good logic, not only in your controllers, but in the operators who are driving the plant. Let's take a look at this. This pump is going to start up. It's going to have a pressure indicator downstream of it, and it's going to have feedback into the logic controller that tells the pump whether to stay online or not. You're going to have valves that control the inlet flow to your vaporizers. Now, on the outlet of these vaporizers, you're going to have temperature indicating controllers. Temperature indicating controllers will feed back to this valve to say how much to open or close, and it'll also feed back to the heat supply for these vaporizers to how much heat to put in. If this temperature indicator controller sees too low of a temperature, it will shut down this vaporization train. Let's say it's set to maintain 40 degrees Fahrenheit by controlling how much hot WEG is fed to this vaporizer. Well, if it sees 30 degrees Fahrenheit, it's going to give a command to send more hot WEG here. But if it sees 20 degrees Fahrenheit, it's going to start pinching down on this valve. If it sees 10 degrees Fahrenheit, it'll shut down the entire train. So this entire vaporization train will be shut down. And one of the problems that you have here is that this temperature indicating controller uses a temperature indicator. And if it's a single temperature indicator and it malfunctions, it can shut down this entire train due to a malfunction. So it's quite common to do a more expensive type of system here, which is called a voting system, where instead of putting a single temperature indicator, you use three temperature indicators, which is three temperature indicators. I want to get that in the screen. There you go. Three temperature indicators, and it does a voting where 2 out of 3 tells the controller what to do. So if one of them is reading 10 degrees and the other 2 are reading 40 degrees, it ignores the one and it goes with the voting system of the 2 out of 3. That's a more expensive way to operate, but it's a much more reliable way to operate. Now, there's another temperature indicating controller here, which is a more serious one, because this looks at the output of the plant itself. And now if this one shows, let's say you have a single indicator here, and it shows 10 degrees, it's going to shut down all 3 trains of vaporization. So this is a serious one here. And this one for certain would be wise to use a voting system where you use 2 out of 3. This way it makes sure that you don't have a spurious or faulty sensor give you a total plant shutdown. And then restarting the plant, getting it back online can be problematic as well. The outlet valve, of course, the mechanic single point failure. You have the fire gate valve, and all the fire gate valve also is looking at fire signals, and it says, "Hey, there's a fire. I want to shut down." It's going to shut down due to a number of different inputs that it could have, and you want to make sure that voting is used for that valve as well, so that you don't get a fire gate shutdown of the plant system. So control is extremely important. This is another thing. Why is this internal tank valve closed? Well, it could be due to a sensor, a single point sensor that triggered and caused an ESD. There you have to look at how many sensors do you want, and how much voting do you want? Now, all of this raises CapEx and raises OpEx, but you have to consider that if you're looking at reliability. Of all of these that I've mentioned so far, probably one of the most important that I have not mentioned yet, but I will now, is reliability by training. The operators that are on site need to know how to operate the plant properly, need to know not to hit that second pump button unless they know why the first one seized, need to know how to set up the controllers to make sure that the vaporizers do not shut down for an erroneous signal, need to understand how the distribution system operates, even though it's outside their plant. I'll give you a for instance of what happened once. I was a Sunday morning. It wasn't very cold out. It was maybe 20 degrees out, 20 degrees Fahrenheit. And I get a call from the system control center. That's the distribution system control center. At that time, I was chief engineer. And he said, "Steve, we're going to lose part of the territory." I said, "Why?" He said, "Because the LNG plant won't give us enough pressure. I keep asking for more pressure, and they just won't they just won't put out any LNG vapor." I said, "Have you been in total communication with the operator at the plant?" "Yes, you have." I said, "Let me call the plant." So I call plant operator who's in the control center. I said, "What's going on?" He says, "Steve, if I put this plant up to any higher pressure, I'm going to blow the relief valves." So I asked a very simple question. I said, "Where are you reading the pressure?" And he says, "At the outlet of the LNG pump. See this pressure indicator?" I said, "Well, that's the wrong place to read the pressure. We have to be looking at the outlet of the plant. Do you have any outlet? Do you have any LNG being vaporized?" He says, "No, because I'm having trouble getting the vaporizers online. And if I keep closing down this outlet valves any further, I'm going to blow the relief valves on the outlet of the pumps." So now I'm realizing the problem here is communication. And there's no cross training between the distribution control room personnel and the plant control room personnel, because the distribution control room person, saying giving more pressure, and the plant operator thinks he means at the outlet of the pump. So what I told him to do is I asked them how these vaporizers are set up. They were all set in automatic. I said, "Shut 2 of them down, put one on manual." I said, "And start opening up this valve." He did so, brought this up to full flow. I said, "Now put the second one on manual and bring it up to full flow." He did so, brought this up to full flow, got this online. I said, "Now put this pump on and set this one on automatic." And it automatically maintained the pressure that was desired at the outlet of the plant. And the key reason why I wanted one on automatic and 2 on manual was so that they don't fight each other. That's what the problem he was having when he was operating with them all on automatic. One would pop up, flow increase, and cause the other one to drop down. This caused the other one to drop down, and the other one would drop down, and one would pop up, another one would drop down. Two on manual and one on automatic is a good mode of operation. It may not be your mode of operation for your plant, but it's the way I was able to resolve this problem real quickly. We got the distribution piping back up to normal pressure, and we did not lose any of the system. Now, this plant was about 300 miles from where I was sitting, and it was a Sunday morning. 9 o'clock the next morning, I was at the plant, and we held a training class. I gave a training class on how pumps operate. And the first thing the plant superintendent asked me is, she said, Steve, when a pump is at its highest pressure, it's flowing at its highest flow rate. Is that correct? And I said, no, just the opposite. We went over what we went over earlier here, the pump curves and how they operate, gave the operators an understanding of how the plant was to operate, how pumps operate, and how vaporizers operate. So training is a critical component of plant operability, but also communication between the distribution control personnel and the plant control personnel is exceedingly important. Just a final word on reliability. Reliability is costly. It increases CapEx during the construction of the plant and repairs of the plant, or during changes you make in the plant, and it does increase OpEx. But with all the CapEx and OpEx you spend, if you do not invest in your operators by making sure they are trained properly, this CapEx and OpEx expenditure can be all for naught. Think of it this way. These are the people that are on the front line at 2 a.m. in the morning, when supervision may not be available at higher levels, when seasoned operators may not be available at higher levels. These operators have to be able to think on their feet, be able to understand the incoming data, and be able to analyze it and make right decisions. A wrong decision at 2 in the morning can pay big consequences and end up in an outage. Also, in order to vaporize, you must make sure that your plant is still there at the end of the day, meaning that you have to have everything else that supports your operation: good public relations, good government relations, abiding by code requirements, etc., to keep your plant open. This is a plant that was totally built. Its first cargo, this was an import terminal, its first commissioning cargo was en route to the plant when its operating permits were pulled. And that was because of poor, or let's say inadequate, public and political liaison. Both of these are carbon. One is of great value, the other is nearly worthless. The same is true with an LNG facility. It can be of great value to your distribution company, or it can be worthless if it's not available to vaporize when needed. These are two separate plants. One has been in operation since 1968, and the other one has been shut down before it even opened in 1973. What made the difference? How the planning was done, the public relations, the government relations, and the investment decisions that were made in building the plant. So some additional things to consider when planning your vaporization project or your vaporization equipment is that it's much more cost effective to spend the money up front and get detailed RFPs than by making changes after the contractor is selected. If the contractor clearly understands his or her risks, he or she does not need to build in much risk contingency. Design it right. Put in sufficient redundancies. Design it with sufficient isolation valves and crossover valves. Make it operable for all projected modes of operation. I'm not saying to gold plate it, but make sure it is safe and reliable. You cannot be reliable if you're unsafe. So the plant needs to be reliable, safe, continuous learning, continuous improvement. That's the pyramid. The very bottom of the pyramid should be plant safety. On top, the next layer is plant reliability. On top of that, continuous learning. On top of that, continuous improvement. Consider the future needs for plant expansion. You may have a 10 million standard cubic foot per day capability today, but you may need 20 million in the future. So when you're building out your plant, think about leaving additional space or additional header connections so that you can expand into the future. Think also about your tank size. If you're vaporizing at a rate of 10 million an hour, at full rate, you could only, if you have a 1 BCF tank, you can't even vaporize for 5 days straight. So consider your needs for expanding the plant itself to higher capacity if that's going to be what's needed in the future. Also, make sure that you analyze how far you can draw down your tank before you might affect your ability to be at full send out. Consider what can happen if you are at full send down. Such things as negative pressure in your tank. Well, that'll certainly shut your vaporization system down. As you draw down a tank very quickly, the vapor space needs to have makeup gas if the boil off is not significant enough. How do you do that makeup gas? Well, one way is to run pumps on recycle. Another way is to actually have vaporized LNG go into your tank, is if that provision is available. Things to consider are things like training on drills, so that as you're vaporizing, you will have drills and have your plant operators run through what if scenarios. What if I get a gas reading inside my expansion tank for my WEG circulation system? Well, how would you handle that? The time to find out is not when you're vaporizing, but when you're testing your equipment. Speaking about testing your equipment, think about what you do before the winter starts. You should get all of your equipment operational, get every piece of equipment tested, and then bring the plant up to, and this is a good practice, the full capacity, which means make a hole in the distribution system where the gas can go. Bring your plant up to full capacity and a full rated capacity, I should say, because it would be illegal to go beyond the rated capacity, but bring it up to full capacity and keep it there for at least a good hour. You'll be amazed at the things you can shake out. You may find that your substation fails. You may find that your odorant system fails. Things that you wouldn't have expected. May not be within the actual LNG plant itself. It may be that your piping on the outlet of the plant can't handle the gas. So there are many things that you need to do to prepare the plant to make sure that when peak day comes, you are available. Consider strongly the 2 out of 3 voting criteria that we spoke of earlier, because that can make the difference between a successful vaporization event and an outage. Other things to consider about vaporization is to bring staff on board early during the construction of your vaporizers or the modifications of your vaporizers. This way they can see it from the ground up and understand it better. Plan on a robust training and retraining program. Keeping people retrained is exceedingly important, especially in a plant that's called on very few times a year to vaporize. Bring the plant online for training purposes early in the season so that they can bring the plant up to full vaporization capacity and operate it for a period of time and see how it performs and get used to making changes, swinging from one pump to another, from one vaporizer to another, etc. Make realistic cost estimates for any improvements that you need at the plant to make sure you improve reliability or keep it to a level that is acceptable. Make sure you have a qualified owner's rep for any changes that are made to the plant. And whatever changes are made, make sure that the system gets tested after those changes are put in place. In the event a crisis or an occurrence happens at the plant, make sure you do a lessons learned exercise and put to work those lessons learned. Also, learn from the mistakes of others. If you hear of a plant that has a difficulty, learn more about it so you can bring that message home and you can become more reliable in your vaporization initiatives.
This just gives you a snapshot in time of how many facilities there are in the United States. And you can see, in summary, there's about 71 peak shavers, 23 satellite facilities, 26 base load, 40 mobile or temporary, and 8 other types of facilities. A good amount of these are clustered in the Northeast, and that's because during the 1960s and 70s, when LNG was making a real inroad into this country, many peak shavers and satellite facilities were installed in the Northeast. And much of the Northeast is dependent on those LNG facilities, those LNG peak shavers and satellite facilities.
For vaporization, initial or expansion projects, design them and build them right. Provide for the pipes and vessels to be cleaned out during construction. Critical design parameters, make sure they are using a 2 out of 3 voting system. Ensure that piping blowout before commissioning, making sure that no debris is left in the piping. Provide for valve tightness tests before commissioning the systems. Ensure proper actions are taken before, during, and after commissioning. Once you own it, don't break it. Build it and operate it correctly. Training, training, training. I can't say enough about that. Do vaporization drills and ask the operators critical questions. For instance, I was at one class and I asked, if you got called by the dispatcher now and asked to put on vaporization at such and such level, how long would it take you to start vaporization? I got answers anywhere from 5 minutes to 16 hours, and both were correct. If your plant is in the cool down mode, your pumps are cold, your line from the pumps to the vaporizers are cold, your vaporizer header is cold, it could take you 5 minutes to get vaporization online. But if your pumps are in a warm state, it takes at least 8 hours of soak time for your pump to get prepared for operation. And it takes another 4 hours to actually bring that LNG into the pump. So you end up with there's 12 hours right there. Then you have to cool down the piping. You have to cool down the LNG header that goes to the vaporizers. And then then you can start vaporizing. So what was correct? 5 minutes? Yes, that's the most optimistic if everything's cooled down, or 16 hours if everything isn't cooled down and ready to go. Everyone needs to know the plant readiness. There's no excuse for a distribution control center not knowing the readiness of the plant, because at any time there could be a pipeline damage that occurs on the transmission piping feeding the territory, and even during the summer they may have to call on LNG to come online. Well, they need to have somewhere written down the lead time that they need to tell the LNG operator to get the plant online. So that if you know there's planned construction on a pipeline, you may want to cool down the plant piping, get it ready for vaporization. And then if there's no such planned construction, then the pumps could be warmed up and the plant maintenance can proceed as needed in order to make the plant ready for the upcoming winter season. Planning on training is extremely important. Okay, so now you've spent $150 million on a plant. Don't break it. Training and retraining is essential. Ideally, your staff will have prior experience. If it's experience from a different company or from a different part of the country or part of the world, make sure you get rid of any bad habits that they may bring with them. You need to train them to the culture of your plant. Ideally, staff will be part of the construction inspection team, so they'll have prior knowledge of how your plant is built from day one. Training should be in compliance with the code, but realize that is just a minimum requirement. Emergency training and drills are essential. Have groups get together and look at, okay, what if situations. Practicing what if situations sharpens their skills. Emergency training and drills are essential. All anomalies that occur during plant operations should be resolved by a joint engineering and operations review, and where needed, even a third party review. And you should always do a lessons learned so that you don't duplicate the anomaly. Implement a quality assurance and quality control program. That should be part of your plant's operation. And actually, it's best to have that report through a different chain of command so that you don't have operations, maintenance, and QA/QC reporting to the same person. This way, it gives some independence and non-bias to your QA/QC program. Implement a condition monitoring program that looks at tribology, that looks at vibration sensing, and looks at thermography for looking at plant performance. Operators should understand not only the procedures, but also the process that is occurring in the plant. Culture of safety prevents anomalies. This is the Skikda plant in Algeria, and as you can see, it was significantly damaged. This occurred when mixed refrigerant got sucked into a boiler. In the United States, the requirement is that such boilers would have a shutdown device at the inlet of the boiler air that says if a hydrocarbon is sucked into the boiler air, the boiler would be shut down. This particular boiler did not have that device. Lastly, examine your corporate risk tolerance and adjust the plan accordingly. Is there sufficient budget to maintain it safely? If not, then don't build it. Would your company rather build pipeline capacity instead of building an LNG peaking facility? Would your company rather use a different form of peak shaving, perhaps underground storage or some other form of peak shaving? Live up to your corporate values. Something interesting here, you'll notice only one value is shown. Do not allow unsafe conditions due to a lack of budget, and that's the corporate value of integrity. Do not cut staffing to unsafe levels due to a lack of budget. Again, the corporate value of integrity. Do not cut continuous learning and improvement due to a lack of budget. Again, the corporate value of integrity.